Welcome to the Newton tutorial series. I'm Mike Cruz with AC Tech, and in this tutorial I want to talk a little bit more about the group list on the material library. I had planned to discuss all of this in the last tutorial, but I forgot to talk about the time step index, so I wanted to expand a little bit more on what that's for and how you would use it. So if we go to our 30 to 60 millimeter particle set and we look at our minimum time step, you recall that the minimum time step is the time step that Newton would use if it ran a simulation using this particle set and these parameters. And that minimum time step is based on whichever cluster in the particle set is most restrictive. So each particle, each cluster, has its own ideal time step that we would calculate. And that time step you could calculate based on the minimum time step and this index. You simply take the minimum time step times the time step index. So that means that this cluster, whichever cluster has a time step index of 1.00, that one is your most restrictive cluster. That's the one that's limiting the size of this time step. And for this particle set, it's been optimized, and we see that our time step index, it only varies by a little bit. So the fastest that we could go here is about 7% faster than this, which is not very significant. And it's also important to note that while the ideal case would have a time step index of 1.00 for all of these clusters, that's not necessarily gonna result in a realistic particle set. Because a real particle set is going to have different size clusters, it's going to have different radii of the spheres in those clusters, it's going to have different numbers of spheres in those clusters. And the more realistic, the more variability in the size and the radii, the larger the differences in the time step is going to be. And also the larger the simulation time index will be. So there's a trade-off between creating a complex particle set with lots of different sphere radii and also maintaining a reasonable simulation time. And you have to determine for yourself what that trade-off, what is the best combination of different radii and different cluster sizes works best. So if I were to take this 30 to 60 set and, well, why don't we move it to the end and then create a copy of it. We'll call this 30 to 60 test. So for this test one, I'm going to take in just this first cluster and reduce the cluster size by 33%, from 61 down to 40. So our sphere radius for these spheres decreased by about 33% as well, from 15 down to 10. And if we look over at our time step, we see, well, the time step index, we're now being limited by this first cluster. This is 1.00. All the rest of these clusters would prefer to use a time step that's about 60% larger, back in the neighborhood of that 147 microseconds. And if I compare this to our 30 to 60 set, so the simulation time index for the 30 to 60 was 3500. With this new set, it's almost 3 times that much. And that's entirely caused by the change in size for this cluster. But in order to create, as I mentioned, to create the variability, to vary the sphere radii, you're going to end up with the difference in the simulation time index. But now what about, instead of changing this from 61 down to 40, what if we change it just from 61 to 50? Now our sphere radius is only 1.3 times smaller. And our time step index, instead of looking at 1.6, now we see 1.25 is our average there. Our simulation time index is now 5500. So going from 3500 to 5500 is reasonable. Going from 3500 to 9000, like we had before, you can decide whether that's reasonable. Is that a good trade-off for being able to use these smaller spheres? So what if we look at a different case? What if we want this particle set to include a very large cluster? So let's just take the same particle set and let's create a big cluster. Let's say auto cluster creator, let's call it 6 by 6 by 6. So just a cube with 216 spheres. Now if I go to my test cluster, let's just change this first cluster to that one. Now obviously, because of our small cluster size, the sphere radius is tiny. But again, what we want to do here is we're trying to look at the idea of creating a big lump. So let's put that cluster size to something more realistic. Why don't we try and match our cluster size so that it matches the sphere radius with the rest of these? So what would that be? Say 300, 260, 250, 240. Alright, 240. So that means now we have approximately the same size spheres in this cluster as the rest of these. Now if we look at our time step index, we see, wow, all of these other clusters want to use a time step that's twice as large as this one. So now, if you recall, in our other particle set, our minimum time step was 147, and that was pretty well shared by all the clusters. But now in this one, we can see that this single cluster with 200 spheres, that wants to use a time step that's over twice as small as the rest of these. And that's directly because of the number of spheres in that cluster. So if you want to use a large lump like this is one way you could do it. You could simply say, well, let's maintain that same sphere radius. That way our sphere size ratio stays the same. And let's just increase the number of clusters to physically make it bigger. But now what if we didn't want to do it like that? What if we wanted to do an extreme case at the opposite end of the spectrum? What if we create a copy? We'll call this 30 to 60 test 2. Now instead of using 216 spheres, what if we just wanted to do one single sphere? What if we just made that one sphere? So now it's the same size, but it's just a single sphere. Well, spheres in clusters, number of spheres in the cluster is 1. Our cluster size is still 240. Our time step index is now actually much, much faster. So the point is, because it's one sphere and because the sphere is huge, the time step for this sphere is very large. Because this is just like if I went to my spheres only 200 millimeter set, because it's approximately the same size. But still, now we have a huge sphere size ratio. Now that's up to a factor of 8. And because of that sphere size ratio, the simulation time index has increased. So looking at our base case, this was 3500. This is now 4600. And something that you should note is that the relationship between the sphere size ratio and how that exactly affects the simulation time is really tough. Because as I mentioned in the previous tutorial, the sphere size ratio is going to determine the grid size that Newton uses when performing the calculations. And because it's different for every single particle set, you can't exactly say, well, if I double the size of the grid cell, I know that the required simulation time is going to exactly go up by a factor of 2 or 4 or 8. You can't do that. You certainly know that when you change that minimum time step, if you cut the time step in half, you double the time for the simulation. That's easy. Similarly, the number of particles in the simulation is kind of approximately linearly related to the simulation time. So we have a pretty clear relationship. We had mentioned that it was each time you cut the size of your particle set in half, if you scale it by 0.5, your time index is going to approximately double. But that relationship for the sphere size ratio is not as clear cut. So when we look at something like this and we have this factor of 8 and we say that, oh, the simulation time index is 4600, that's a little hazy. It could be anywhere in the range of 3500 to 10,000. It's really tough to approximate it because it depends very heavily on this specific particle set, and we haven't run a bunch of tests using a particle set like this. So the point is that rather than using 216 spheres or using a single sphere, what if we pick something that's kind of in between the two of those so that we don't have quite so many spheres, but at the same time we have a more realistic looking shape than just a giant sphere? Let's go back to our cluster creator and let's make a 4 by 4 by 4. Alright, so now this only has 64 spheres. So now what if we take, where's our test? There's our test. Move to the end. Let's create one more copy of this. 30 to 60 test 3. Now we set our first lump as that 64. Now if we compare this to the test, again, both of these clusters have the same cluster size. So this has 216 spheres, and this new one has only 64 spheres. And you can see that those spheres are physically bigger. You know, our sphere size ratio is 1.6. Cluster is the same size, but now our time step index, rather than being, if we look at this other one, this was our most restrictive cluster. But now going to this cluster, because our sphere radius is bigger, the time step index for this cluster is actually larger than all the rest of them. So that means that the simulation wants to use a larger time step for this cluster. And that's because while the number of spheres has increased, you know, it's not 2 or 3 or 4, this is 64 spheres, but the sphere radius is also significantly bigger. So that bigger sphere radius means that we can have a larger time step for this whole cluster. And of course, the fact that this radius is bigger means our sphere size ratio is no longer 1.0 like it was for this other particle set. But looking at the simulation time index has still decreased. Overall, our particle set is still 147. We still have a cluster that is 240 millimeters, but that cluster no longer has 200 spheres. So the net effect seems to be that this particle set will run much faster than this particle set. And of course, to confirm that, you would have to run some test simulations and say, well, does this actually hold true for this specific cluster? Can I run a simulation, you know, that runs about 3 times faster than this simulation? Because as I mentioned before, that the relationship between that sphere size ratio and the simulation time is pretty hazy. It's pretty tough to determine outside of simply running tests to confirm that. So the point here is, when you want to create a particle set with big clusters, how should you do it? Do you want to use a whole bunch of spheres, or do you want to use a few huge spheres, or maybe somewhere in the middle? And we think that definitely the best way to do it is somewhere in the middle. Because if you have a couple of larger lumps that have a slightly larger sphere radius, you know, like we said, your sphere size ratio is going to go up. You no longer have identically sized spheres. But you still don't end up with clusters that have 5, 6, 7, 800 spheres. So the net effect on your simulation is going to be modest, and you can still create a decently shaped cluster. You know, if I wanted to take this same number of clusters, I could create a bunch of different shapes using 64 clusters. However, using a single sphere, I can only create one shape with that cluster, and it's going to be rolly, and it's not going to look realistic. So you can decide how you want to create your clusters, your lumps, but we recommend trying to follow this model where the sphere radius for these lumps, try and keep it anywhere between being exactly equal to these and maybe being twice as large as these. So keep that sphere size ratio under 2, and then you'll be able to still create huge lumps that don't use a ridiculous number of spheres. So I think that covers everything else I wanted to talk about for this group list. So the next tutorial will talk about the other features of this library window. If you have any any questions about these lump sizes or this group list window that's not addressed in these tutorials or in the manual, go ahead and send us an email at info@actech.com. Thanks.